Let us derive the equation for competitive inhibition based on the inhibition mechanism shown below. In the absence of an inhibitor, the enzyme first binds to the substrate at a rate of K1 to form the ES complex. The ES complex can either dissociate back to free enzyme and substrate at a rate of K-1, or proceed forward to form product at a rate of Kcat. The Michaelis-Menten and Lineweaver-Burke kinetic equations that represent this type of mechanism are shown. We now examine how the presence of a competitive inhibitor alters these two equations. In its presence, because the competitive inhibitor is structurally similar to the substrate, it competes with the substrate for binding to the enzyme's active site to form an EI complex. In addition, because the inhibitor and substrate compete for the same active site, formation of an ESI complex is not possible. Thus, deriving the kinetic equation for competitive inhibition requires accounting for the additional EI complex in a reaction scheme. Because this approach is similar to that used to derive the Michaelis-Menten equation, it is recommended that you review it beforehand. Since Kcat, the chemical step, is the slowest and thus the rate-limiting step in the reaction, the velocity is equal to Kcat multiplied by the concentration of the ES complex. Regardless of the presence of a competitive inhibitor, the velocity of the reaction does not change and is equal to Kcat times the concentration of the ES complex. Next, write the equation for total enzyme used in the reaction. Unlike simple Michaelis-Menten kinetics, competitive inhibition kinetics include an additional EI complex in the reaction scheme and therefore must be taken into account. Next, the rate of an enzymatic reaction depends on the amount of enzyme used in the reaction. As the amount of enzyme in the reaction increases, the reaction velocity increases accordingly. Therefore, one must take this into account by dividing the reaction velocity by the total enzyme concentration used in the reaction to obtain the equation shown. After division, the concentrations of the ES and EI complexes in the resulting equation are unknown and cannot be measured directly. If the catalytic step, Kcat, is small compared with the other steps, it can be neglected and the rapid equilibrium assumption can be applied for the formation of ES complex. According to the law of mass action, the ES and EI complexes can be expressed in terms of measurable parameters as shown. If the catalytic step, Kcat, is small compared with the other steps, it can be neglected and the rapid equilibrium assumption can be applied for the formation of ES complex. According to the law of mass action, the ES and EI complexes can be expressed in terms of measurable parameters as shown, which can be rearranged as follows. Now, substitute the expressions for the ES and EI complexes into the equation above. From this point on, regardless of whether one is deriving the equations for simple Michaelis-Menten kinetics, competitive inhibition, non-competitive inhibition, or uncompetitive inhibition, the same steps are used in the following order. First, simplify the equation by canceling all terms containing free enzyme E. Second, rearrange the equation by moving ET to the right-hand side and replacing ET times Kcat with Vmax. Third, multiply the numerator and denominator on the right-hand side of the equation by Km. Finally, after some rearrangements, factoring out the term Km. Comparing the Michaelis-Menten equation in the absence of a competitive inhibitor with that in its presence, one notices that the competitive inhibition equation contains an additional 1 plus I divided by Ki term. The term 1 plus inhibitor concentration divided by Ki also appears in the Lineweaver-Burke equation. Comparing the Lineweaver-Burke equation with the general form y equals mx plus a, the slope m contains the inhibitor term. Therefore, in a double reciprocal plot of 1 over V versus 1 over S, the slope M changes in the presence of a competitive inhibitor, whereas the intercept A does not. As the concentration of the competitive inhibitor increases, the slope becomes steeper. Thus, competitive inhibition can be identified from the 1 over V versus 1 over S plot by comparing data collected with and without an inhibitor. If the slope changes while the intercept remains unchanged, the inhibitor is a competitive inhibitor. Similarly, in a plot of V versus S, Km changes while Vmax remains unchanged in the presence of a competitive inhibitor.